So yeah, we want to expand those definitions that we've had for our six trigonometric functions and turn them into a broader definition. And the main reason is, well, there's lots of reasons, but the one that we'll focus on is that for right now, because we're stuck in a triangular definition, our angles that we care about are only able to be angles that can live inside triangles, and that's fairly restricted. We can't have an angle that's larger than, well, since it has to live in a right triangle, we can't have an angle that we're talking about here larger than pi over 2 radians or larger than 90 degrees. So we're kind of stuck, and we know our angles go a lot further than that. So we want to go here and we want to expand them so we can use them on any of our, how do I get that started? That's fun. So, we'll say that's a circle. So we want to expand them so we can use them on any of our, that's better, angles. So instead of defining our angles based on, or our trig functions based on those triangles, we're going to define them on angles as they go around in a XY coordinate system. And we're going to need a circle to help us do that. One of the goals of these new definitions is going to be, we want to have this expansion without changing what we already know. We don't want our old definitions to be hurt by this or be destroyed by this. We just want to add to them so that we have more to work with. So what we're going to need to do here is, for any angle theta in standard position, instead of defining our trig functions based on the sides of a triangle, we're going to base our trig functions on the radius of this circle, and this circle will be able to be any radius. We'll often treat this circle as radius 1 for our convenience when possible. But define it on the radius of that circle and the XY coordinates of where the terminal side, the ending side of that angle, intersects the circle. Now you can probably see here that the reason this isn't going to disrupt our triangular definitions is, if we drop a line down from that intersection point, it forms a little right triangle. So that opposite side of that right triangle, the adjacent side of that right triangle, and the hypotenuse of that right triangle, our definitions for our trig functions should stay consistent with those, but allow us to take this angle past where it would be able to live in a right triangle. So keeping that in mind, let's define our trig functions. Use that one. So our sine function of any angle, instead of being opposites and hypotenuse, we're going to use the XY coordinates and the radius. So it's going to be the Y value of that intersection in ratio to the radius of the circle. So it's going to be Y over R instead of opposite over hypotenuse. It's the same ratio, the same setup, but we're going to be able to use it more generally. Correspondingly, our cosine of theta is going to be the X value in ratio to that radius. X value in ratio to the radius. And our tangent will be the ratio between the y value and the x value. Between the y value and the x value of the point of intersection on our circle. So we can think of this as, instead of dealing with, if we want to think of it geometrically, instead of trying to deal with what are the ratio of side lengths in a triangle, we're essentially looking at, as we rotate through different angles, what is the vertical versus horizontal displacement in ratio to the radius. So we'll kind of start associating the sine with y values, with vertical displacement, and cosine with x values, horizontal displacement, in ratio to the radius of the circle. If we consider the radius of that circle to be 1, if the radius is equal to 1, we get to further simplify these a bit. If that radius is 1, then that r is a nice 1, this r is a nice 1, and we start looking at our sine function just being that y value, as long as our radius is 1. The cosine being the x value. Now the tangent doesn't have an r in it, so it would still be y over x. But we'll often use and refer to the unit circle definition of our trig functions. When we hear that unit circle definition, it's referring to a circle of radius 1 unit. So on our unit circle, our sine value is just the y value. Our cosine value is just the x value. The tangent, their ratio. By the way, if this looks a little bit like slope, change in y over change in x, there's a reason that that looks like slope. But you'll work more with that in calculus. But if that jumped out at you, that's a good thing. So let's jump here right into an example. Let's say we have a circle, and that circle is on an axis. And we are told that the terminal side of our ray of our angle, let's put it down here, goes through a particular point. So the angle we're talking about here is this angle, theta. Now, you certainly could not have a triangle with this big angle in it. That's more than 180 degrees. A triangle cannot exist with this angle. So if we wanted to have our trig functions defined for angles this large, the triangular definition wouldn't work, but this one will. So let's say, just for ease, let's make some numbers nice, that the intersection point, or there is a point on that line that passes through, let's do that, -4, -3. So that point is on this ray. Now, whether or not there's a circle here, certainly we could draw a circle here if somebody didn't do it for us. And if we want to define these trig functions, or want to find the value of those trig functions, we'd have to find what the radius of that circle is. Well, if the point -4, -3 is on that ray, then we certainly know that this raw physical length is 3. Now it is in the negative direction, so I'm going to keep it -3. And we know that this physical length is -4. So do we have a tool that would allow us to figure out what this length is? knowing the y displacement is -3 and the horizontal displacement is -4? Might not be a tool that we're used to using with negative numbers like this, but what could we do to find that radius of that circle? I'm gonna let you guys answer that. Dominic, Pythagorean theorem. But wait, Pythagorean theorem is positive numbers with triangles? Well, there still is a triangle here. This has a length of 3. It's just in the negative direction. This has a length of 4. It's just in the negative direction. So we can absolutely still use Pythagorean theorem. The -3 squared plus -4 squared is going to be equal to the square of the radius of that circle. So 9 plus 16 equals r squared. 25 is our r squared. So our r is plus or minus 5. Now we're always going to consider our radial lengths positive. The radius of our circle is always a positive length. It doesn't matter which direction it goes in. All the radii are positive. So if we want to find what the sine of this angle theta was, it's not in a right triangle, but that's okay. It doesn't have to be anymore. Our sine value is defined as that y over r. So the y value here was -3. The r value 5. So -3/5. The cosine of that angle, same thing, x over r. That's our expanded definition, x over r. So -4 over r, -4/5. Our tangent, again, our expanded definition, y's over x's. So the y value of -3 over the x value of -4. So -3 over -4, which we would certainly simplify to 3/4. Questions about any of those? So it probably occurs to you that this is not that different from what we were talking about. If we consider this little angle here, that little angle there is not the angle that we're being asked about. We're being asked about this big angle. But if we look at that little angle down here, that angle sort of is, well, definitely is if we draw it, in a right triangle. And for this little right triangle, this 3 is certainly the absolute value of our opposite length. That 4 is the absolute value of our adjacent side to the little angle here. That certainly is a hypotenuse. So these definitions aren't completely different. We can kind of still think of them as, oh, it's opposite over hypotenuse, it's adjacent over hypotenuse, it's opposite over adjacent. So having our right triangle definitions down solid is still super, super important and helpful. And it doesn't really change much about our intuition, except that we're now allowed to have these lengths be negative. And we're allowed to consider them for larger angles just with the same logic. By the way, this little angle has a name. Of course it does, right? Everything has a name. We label everything. So if our angle is this big angle theta, the acute angle measured between the x-axis either positive x-axis or negative x-axis, depending on which way you're looking. But the acute angle measured from the x-axis to the terminal side is called theta's reference angle. Ref angle. So you'll often be asked about reference angles, like what's this thing's reference angle? So for sake of argument, if theta was, let's say, 215 degrees, well, then that reference angle would be the 180 minus or subtracted from the 215. So that would be 35. 35? Yeah, 35. So the reference angle, often written theta prime, little apostrophe on it. So theta prime would be that 35-degree reference angle. Always positive, so always measured in the positive direction, and always between the x-axis and the terminal side. So for example, if our ray ended up here, we'd measure it still positive, but to the positive axis instead of the negative axis. So we'll throw that reference angle, language around a lot. And the reason we like the reference angle is because, all of our sine, cosine, tangent values for the 215-degree angle are going to be the same as the sine, cosine, and tangent for a 35-degree angle, except that they might be negative instead of positive. So these ratios are the same as if you imagine that same angle, but up here with the 35 degrees, here, I should have it go all the way up here. That length is still going to be 3. This length is still going to be 4. That radius is still 5. So we still have 3/5, 4/5, and 3/4. They're just positive instead of negative. So oftentimes we'll at least be thinking in terms of our reference angles, so we can think about it in terms of triangles. Questions about that? As I mentioned, we will often work considering this to be a circle of radius 1. And there are some handy things about that. There are some reasons why we like that. Move that over so I can still see you guys. So if this circle is radius 1, and we know a point on this circle, let me put it up here. You know a point on that circle. Say the point on that circle of radius 1 that we know, let's say it's -5/13 and 12/13. So let's say that point is on the circle of radius 1. Well, first and foremost, if I'm saying that that's on the circle of radius 1, you'd have to either just believe that and trust me, always a bad idea, or there'd have to be some way we could verify that that is on the circle of radius 1. How could we test to see if that is indeed on the edge of a circle of radius 1? What tool could we use to test that? What do you guys think? I think I mentioned the other day that the answer to about 70% of the questions I'm going to ask you guys is the same answer. I heard Sam mouth Pythagorean theorem. Yep, I was waiting for Dominic. I was waiting for you to copy and paste. So if we put that into the Pythagorean theorem, we should end up showing that the radius is 1. So for it to be on the circle of radius 1, the negative 5/13, 12/13, oops, the negative 5/13 squared, sorry, plus the 12/13 squared had better equal 1. So if we wanted to test that, then 25 169ths plus 144 169ths had better equal 1. And indeed, it's 169 69ths, 169 169ths, which is indeed going to equal 1. So at that point, if ever you're cautious about, wait a minute, is that circle, or is that on the right circle, or what is the radius of my circle? Remember, the xy and the r will always have this relationship. The x squared plus y squared will always equal r squared. Those of you who just went through Math 111 and dealt with circles might remember that this was the equation of a circle centered at, well, hk, so centered at 0, 0. If we want that radius to be 1 on our unit circle, that means the equation of that circle is, oops, that went too high, can't draw up there. The equation of that circle is x squared plus y squared equals 1. So even if we just knew the x value, we could solve for that y value, as long as we know it's on a circle of radius 1. So the nice thing about being on the unit circle is that if we ask, hey, what's the sine of an angle whose terminal side goes through that point, it actually doesn't matter whether we rotated this way or whether we rotated, say, negatively to get there. As long as our initial side is from the positive x-axis, the fact that this is a negative angle doesn't change what our definition is. The sine of that angle, I'm going to call that angle phi. The sine of that angle phi, normally we'd think y over r, but because we're on the unit circle, it's just the y value, 12/13. Cosine of phi, the x value, negative 5/13. The tangent will be a little bit more fun here because the tangent's going to be that y over x, so 12/13 over negative 5/13. But the nice thing, multiply by 13 over 13, that's going to naturally reduce the 12 over negative 5, or negative 12/5. So you really quickly want to start associating the sine function with y values, the cosine function with x values. If we're in a scenario where this radius isn't 1 and the radius is something else, that's okay. Just divide by that radius value, essentially brings that ratio down to a ratio of 1. In case you're curious, by the way, where I came up with the 5/12 and 5/13 and 12/13, We dealt with a couple of days ago one of our triangles that had some nice lengths on it. It had a length of 5 and 12 for the legs and 13 for the hypotenuse. This is one of those famous Pythagorean triples, one of the few triangles in which all the side lengths can be nice whole numbers. Usually side lengths are horrible numbers. That means that there is, if we make a circle, I like those better. If we make a circle of radius 13, so if that radius is 13, we know we can fit a triangle in here where that's 5 and that's 12. Fair? So all we have to, and we could define that point up there. That point up there is, ooh, sorry, didn't want that. This point up there would be the point 12, 5, and we could define our trig functions based on that. The 12 thirteenths and the 5 thirteenths as the x over r and y over r. But we could always make a little circle here of radius 1. And if we make that little circle of radius 1, all of these values just become 1/13 the size. So this radius went from 13 to a radius of 1, my radius of 1. This length of 5 turned into my little length 5/13. And this 12 shrunk down, became 12/13. So if we just dividing out that radius to get those lengths. So it's almost like, okay, are we doing y over r? Or are we shrinking things down onto a unit circle by dividing everything by the radius and just using the y value? Either way, it's the same ratio. Does that seem reasonable? So again, these definitions are essentially equivalent, and our triangular definition is just a restriction to acute angles, but even that can extend into reference angles. Questions about any of that before we mess with it a bit, see what we can do with it? All right, let's play a little bit. I want another big circle here. Ugh, too high. I can't argue that it's not somewhat handy being able to have this thing draw circles for me. So I want some different rays here, and I want to color code them. I want a ray coming out through quadrant 1. I want a ray coming out through quadrant 2. A ray coming out through quadrant 3. And a ray coming out through quadrant 4. Now, all of these are still being measured in one way or another from our positive x-axis. So that standard position is an assumption for all of these definitions. If you're not measuring it from standard position, we can still use all these tools. We just rotate our environment and have it act like standard position. So that's just almost a formality in our assumption. Like, for example, the one in quadrant 1, it could go all the way around into quadrant 1. I don't want to complicate my picture that much, though. So all of them do have to be measured from that standard position for these angles to be the way we're talking about them. But what can you tell me for this ray, about what the sine of this angle is? What can you tell me about what the cosine of this angle is? And what can you tell me about the tangent of this angle? Now, you can't tell me what the values are because I haven't given you what the coordinates here are. But Felix, absolutely. All of these are going to be positive values because our x values are going to be positive, so our cosine's positive. Our y values are positive, so our sine is positive. Tangent is their ratio, so a positive in ratio to a positive is still going to be positive. So all of our primary trig functions are all positive for any ray ending in quadrant 1. By the way, if we want to extend this to our cosecant, our secant, and our cotangent, I haven't been talking about those today just to keep things a little bit simpler. But we've been really talking about the cosecant less about being how it's defined in terms of hypotenuses and radii and whatnot, and more thinking of it as the reciprocals. So if the sine is positive, then its reciprocal value is still going to be positive. The secant, if cosine's positive, its reciprocal is positive. If tangent is positive, then its reciprocal cotangent is positive. So I won't be referencing those, but keep in mind, what about those other functions? We really tend to think about those other functions just as reciprocals of whatever these are. So even if we look back here, cosecant would be r over y. Secant would be r over x. Tangent would, or cotangent, sorry, would be x over y. In our unit circle, cosecant is 1 over y. Secant is 1 over x. So we really don't need new definitions for those as long as we consider ourselves to be as long as we consider those in terms of their reciprocal identities. So what about over here in quadrant 2? What about the sine of our angle in quadrant 2, the cosine of our angle in quadrant 2, and the tangent of our angle in quadrant 2? Letting the colors differentiate between which ray we're talking about. Are all of them still going to be positive? Che, you're saying no, because that would be boring, right? If they were all still positive. Which ones are positive and which ones are negative, though? Nicholas said negative x's and positive y's. Felix said only sine, in terms of only sine being positive. Yeah, because our y values are positive, our sine is still going to be positive. Our cosine will be negative because of those negative x's that you're mentioning, Nicholas. The tangent, though, because the tangent will be a ratio between positives and negatives, the tangent is negative in quadrant 2. For your own diagram, I hope you're making a similar diagram, decide the positiveness or negativeness. I could have said determine the signs, but that would be confusing. Often we'll refer to it as the polarity, by the way. So what is the polarity? What is the positiveness or negativeness of the value? So for sine, cosine, and tangent in quadrant 3, determine their polarities. And for the sine, cosine, and tangent in quadrant 4, determine their polarities. So down here, our x and y values will both be negative. So ideally, you're happy with the sine being negative and the cosine being negative. But that does make that tangent positive. down here for quadrant 4. Our sign, again, our sign we're associating with the y values. The y values are negative in quadrant 4, so the sign's going to be negative. But we're back to a place where the x values are positive, so that cosine returns to being positive. Tangent is their ratio, and a positive in ratio to a negative, or a negative in ratio to a positive, is going to be negative, so tangent is negative there. It will be somewhat surprising how important this is. Recognizing what the sign of your values are going to be, whether something should be positive or negative, depending on what quadrant we're in, is going to be an important piece of information for a lot of the mechanics that we do. Alternatively, not only knowing what quadrant we're in because of the sign, but knowing the sign because of the quadrant we're in both directions, that's going to be really important. We have some tools that will give us an answer, but it'll give us a plus or minus, and we won't know which one to use unless we know what quadrant we're in. So we'll have a tool that says, hey, the answer is plus or minus this, but it's not both. We have to assign the positive or negative because we have also figured out it's in quadrant 3, so it must have this sign. It's in quadrant 2, so it must have this sign. So these relationships are really important to recognize, but I do want to kind of dissuade you from, just straight memorizing these relationships. You already know them because you know where x is positive. You know where y is positive. You know where x is negative. You know where y is negative. If I asked you is x positive right here, you'd say, no, x isn't positive there. Were you crazy? So if you associate cosine with x's, if you make that association really strong, you don't have to memorize this information. You just know I'm down here, my x's are negative, my y's are negative. That means my functions will be negative for sine and cosine anyway. Is that reasonable? I really do want you guys, there's a lot of stuff we're going to have to memorize in here, but there's a lot of stuff that I don't want you to memorize because it's just too much information after a while. The more information that you can build off of the things we know, the less you'll have to memorize, the less overwhelming it'll be, and the longer you'll retain a lot of it. So try to keep that in mind as you study some of this stuff. There are some mnemonics for this, though. Again, this is quadrant 1, quadrant 2, quadrant 3, and quadrant 4. One of the common ones is, in this first quadrant, all of them are positive. In this quadrant, sine is positive. This one, tangent is positive. This one, cosine is positive. So some of the mnemonics are things like all students take calculus. Or one of the other common ones is, say, a smart trig class. But I don't know that about you guys yet, so can't go with that one. And while all students don't take calculus, all students should. So it's a nice one. So questions about any of that? So one of the ways in which this will come up is you'll see questions like, say, find an angle in the first rotation. Sometimes that first rotation will just say in the interval from 0 to 2 pi. That's the radian values for our first rotation, or if they want degrees, you'd be from 0 to 360 degrees. Notice, by the way, that the 0 is included in the interval, but the 2 pi is not. the 2 pi and the 0 are coterminal. So they both reference that location. Same with degrees, the 0 and the 360 both denote this location. So if we want the first rotation goes up to, but not including that end, because that end double maps that first point. So you will see it written this way. Make sure you know, take note of that. So find an angle in the first rotation that has the same, let's go with sine value, as some given angle. So let's use, how about 5 pi over 6? So this is often often seems like kind of a strange question the first time you try to approach it. But let's look. 5 pi over 6. We know 5 pi over 6 is more or less over here. You guys have been practicing drawing those unit circle diagrams. I mean, right? You guys have been practicing drawing those unit circle diagrams? You have been practicing drawing those unit circle diagrams. You draw that? Sam, you're giving me one of those. Do practice. We want to build that intuition. But just remembering that, pi radians is over here, 2 pi is over there, 5 pi over 6, so 5 6 is less than 1, so 5 6 is a little bit less than pi, so 5 pi over 6 has got to be pretty close to pi. It's a lot more than half. But the quicker you can get those down, the handier you're going to be. Now, we could certainly try to figure out what the sine of 5 pi over 6 is, but we actually don't need to for this problem. We know this angle is 5 pi over 6. If this angle is 5 pi over 6, we know the sine of that 5 pi over 6 is going to be positive, right? Because the sine of pi over 6, because the pi over 6 is in quadrant 2, we know the sine is going to be positive. So what other quadrant has a positive sign? Well, quadrant 1 has a positive sign. So there's going to be an angle over here in quadrant 1 that has the same y value and by necessity the same radius because it's on the same circle as this one does. So we should be able to, conceivably, find this angle, essentially the one that mirrors this angle. So if this angle was 5 pi over 6, and we want, say, how much is this angle here? Remember, we talked about reference angles. So essentially we're asking, what's the reference angle here? Well, that reference angle there would be the other pi over 6. So if we take that reference angle of pi over 6 and move it over here, then that's just an angle of pi over 6. So what angle in the first rotation has the same sine value as 5 pi over 6? Well, pi over 6 does. Fair? They're both going to have that same, it's going to be that same y value over the radius. Or if we're on the unit circle, it would just be the same y value. So they got to have the same value. We could do that again for a different angle. Maybe even not one in radians. We could do it in degrees just as easily. Say angle in the first rotation that has the same, I'm going to stick with sine for a minute here, the same sine value as 312 degrees. Ugh, 312 degrees. Well, we're going to do the same thing. What quadrant is 312 degrees in? Well, 312 degrees is down here in quadrant 4. Now, exactly where in quadrant 4 actually doesn't matter. I'm just going to draw it somewhere down here. That's where our angle is. So this angle is 312 degrees. So we're supposed to find another, I'm going to get some of this stuff out of the way. We want to find another angle that gives us the same answer for sine as that 312 degrees. So the big question, kind of the important first question, is what quadrant must that other angle live in? I'll let you guys answer that. What quadrant must the angle we're looking for live in? And why? Three, because the y needs to be negative? Yeah. We need someplace else. We know sine is going to give us a negative ratio because we're in quadrant 4, because the y values are negative. The only other quadrant with negative y values are over here. So it's going to have to be some ray in quadrant 3. And again, this length has to match that length for the ratios to be the same. So this angle here must be the same as that angle there. We know this angle because we have the other part of it. So that angle has to be, 48 degrees? So this reference angle here, so the reference angle for this is 48 degrees. So the reference angle for this one has to be 48 degrees. If we know that that reference angle is 48 degrees, then if we want the angle in standard position for that ray, it had better be the 180 plus that 48. So 180 degrees plus the 48 degrees is going to give us what, 228 degrees? The sound effects help, I think. So 228 degrees will have that same value. We don't know what that value is, but that's okay. We weren't asked for what that value is. I don't know what the sine of 312 is, but I do know it's equal to the sine of 228. I want to give you guys a chance to try this, but I want you to try it with a different function here. So let's copy that, find, it's probably a way for me to copy and paste this in Zoom, but I don't know it yet. Find an angle in that first rotation. So in the interval from 0 to 2 pi, we'll do a radians one. That has the same, let's go with, it's hard to decide. Let's go with cosine. The same cosine value as, oh, I want to have some, I want to go nuts with it. How about 17 pi over 3? Ugh, it's like I've made that bad or something. So this question is where I'm going to leave you, but I'm not going to leave before we talk at the answer, but that's the last thing we're going to do today. We are out of time today, but do take a minute and try to decide what quadrant 17 pi over 3 is in. Then you got to figure out whether the cosine's positive or negative in that quadrant. Gosh, then you got to figure out what other quadrant has that same polarity. Then you got to figure out the reference angles. Ugh. There's a surprising amount that goes on in that question. So I'll give you a minute to play with it. Garrett, you're thinking quadrant 4? Okay. Actually, I'm not sure. I gotta draw it. Kevin agrees, though. Okay. So if we're talking about pi over 3s, a full rotation is 6. So from 0 all the way around would be 6 pi over 3, because that's the same as 2 pi. So one rotation is 6 pi over 3. Two rotations would be 12 pi over 3. A third rotation would be 18 pi over 3, but we're 1 less than that. So 17 pi over 3. I promise it's a straight line. So 17 pi over 3, yeah, nicely in quadrant 4. It's going to bug me. I got to draw a straight line. Automatically, that we can determine real nice and quickly what the reference angle is. The reference angle is that other pi over 3. Shouldn't the ray be closer to... Well, pi over 3, remember, is 2/3 of the way here. So it'd be 1 pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3. So it should be closer to the y-axis than the x-axis. 11 pi over 6 is the one that's closer there. Nick, does that make sense? Cool. It does seem like a third should be down here, but it's a third of the full 180. Yeah. So what's the other quadrant our other answer should be in? Ooh, I got some argument here. One person said quadrant 1, one person said quadrant 3. Went back to 3. Ooh, lots of competition. I love that. So again, we got to go to the angle. Cosine, or the sine. Cosine in quadrant 4, cosine is positive in quadrant 4. So whatever the cosine value here is in quadrant 4, its value is going to be positive. Whereas the other place that cosine is positive, well, the other place cosine is positive is up in quadrant 1. If we were doing tangent, tangent is negative in 4, so tangent would bring us up to quadrant 2. When we did sine, sine was negative, so it brought us to the other negative quadrant. So do be careful. It's a combination between which trig function we're looking at and which quadrant our ray is in. We can't look at just the function. We can't look at just the quadrant. We got to look at their combination. So the answer we're looking for is going to be up here in quadrant 1, and it's going to have the same reference angle. So the same reference angle of pi over 3. Nice thing about being in quadrant 1, the reference angle is the angle. We don't have to do that whole, figure out what the rest of it was, add it together thing. So our answer just gets to be pi over 3. So the cosine of 17 pi over 3, again, we don't necessarily know what that is. We actually have all the tools necessary. We'll talk about that on Monday. But we know the cosine of 17 pi over 3 is going to be equal to the cosine of 1 pi over 3. Those values, whatever they are going to be the same. Questions about any of that? Went a little over time today. Sorry about that. I got all excited. So if you come up with any questions on any of that, let me know or throw them in the forums. And we'll look at them. Other than that, have a great weekend and have a wonderful day. You're welcome, Sam. You're welcome too, Dominic. Have a good day.